Hello, everyone. My name is Hari, and today we are going to be discussing resistors in the electrical engineering setting. So shown here is a circuit. Circuits are based in protons and electrons and the fundamental forces of electromagnetism, but we're going to be skimming over those today in favor of simply equations and electrical engineering applications. So here we're going to point out a few important things. First, we have a battery, which is one circuit element. As you can see, this battery is associated with 10 volts, so it provides a voltage difference of 10 volts. Then we have resistors, which use the symbol of the ohm for their property, which is the resistance. And you can see it's sort of denoted by a squiggly line. And lastly, we have wires. And wires are just denoted by straight lines. And so one quick thing I'm going to note here is that this circuit, and we're actually going to move to this notes right away here, circuit here, this circuit of a battery and resistor can be drawn in multiple ways. It can also be drawn like this. The fundamental thing is that a battery is here and a voltage is here, and they're connected by two wires. The geometry of these wires does not matter in the slightest. So with that out of the way, we can sort of dive into a few more things about circuits and resistors. So first we're going to talk about the voltage. The voltage of a segment of wire is determined somewhat by the charge on that segment of wire and the speed at which that charge is moving. What you really need to know is that at any point in space or wire, the point has a voltage. When the battery is given a voltage of 10 volts in this example before, it means that point 1 has a voltage that is 10 volts more than point 4. Since point 1 and point 2 are connected by a wire, this means that point 2 has a voltage that is 10 volts above point 4, a voltage that is 10 volts above point 3, similarly. Yeah. Now, give us the slightest of seconds, and we're going to be continuing. Yeah, so here we're going to be talking about resistance. And resistance is similar to voltage, except it has to do with resistors. So resistors also have a voltage drop, but they don't just tell you what the voltage drop is like they do in the battery. Instead, they give you a number of ohms. And this number of ohms is a property fundamental to the resistor itself. Now, we know that point 2 and point 3 are 10 volts apart. So we know that this resistor has a voltage drop of 10 ohms. So what are we looking for? Well, we're going to be using this equation V equals IR, which says that the voltage drop across a resistor is equal to the current through the resistor times the resistance of the resistor. What this means is that we're really looking for the current that is flowing through this resistor. As you can probably tell from an analogy to fluids, or just a common sense idea here, if there's a current going through the resistor, then the same current must be going through any other part of the circuit. So what we'll be using is, since we know that the voltage drop across the resistor is 10 ohms, because the battery voltage gain is 10 ohms, we know that 10 ohms is equal to the current times the resistance. And since the resistance is given as 5 ohms, we know that the current is 2 amps, or 2 amperes. And the ampere is denoted by the letter A, and it's the unit of current. So we're going to be talking about parallel and series resistors now. So the basic idea behind a resistor is that it goes from point A to point B, and there's a current across it. Then there is also an associated voltage drop. If there's no current, then there's no voltage drop. So that's how the resistor differs from the battery. A quick note, you might see batteries seen like this. Batteries might also be seen like this, or they can add however many like small lines and big lines in tandem as they want. They simply have to have at least one of them. So you can carry this out forever if you want. Sometimes each of these pairs signifies a voltage drop of 5 volts, but they'll tell you what it is. So basically what I'm saying here is that don't worry if you see a bunch of these in tandem. It means the same thing, it's just one of them. Right. So you're going to be asking yourself, well, we've seen this case where we have like 10 volts, and then we have 5 volts here. But what if we have another 5 volts? What's going on here? Well, to start talking about this, it's important that we introduce a few laws first. The first law is Kirchhoff's current law, which says that the voltage or the current flowing into any segment of wire is the same as the current flowing out of it. This should make sense intuitively. If you sort of make the analogy to water, if water is coming in here, then the same water is leaving that place. This is with the continuity equation. If you're familiar with that, A1 V1 equals A2 V2. Although it might not be a direct analogy, the same idea is given. So what we're going to be doing here is you can sort of see a similar thing. Like if you have a circuit that branches off into 2 and then returns into 1 and does something like this, and the current here is equal to the sum of the current here and the current here. I equals I1 plus I2. And this should make sense. So what we're really saying is that the current entering this they call it nodes, very similar to nodes in graph theory, but the idea is just it's the segment of wire. The current entering this segment of wire is the same as the current leaving this segment of wire. So that's what's going on there. The second law is Kirchhoff's voltage law, and what this law says is that so what it technically says is that if you have a bunch of elements, let's say they're not squiggly lines anymore, we're gonna make up some symbols. This has a voltage drop. Let's say it's plus voltage. This has a voltage drop. We're just gonna make up our own symbols. The idea is, if you go all around, and then we're gonna make a triangle. This has a voltage drop as well. This says that V1 plus V1 minus delta V2 minus delta V3 equals 0. This makes sense. This place has a voltage. So if you come back to the same place, then the place still has the same voltage. That's what's going on over there. So Kirchhoff's voltage law makes a lot of sense. It's just saying voltage here is the voltage here. There's no funny stuff going on. Right. So now we're going to be talking about series and parallel resistors. And as you can see in the image that we provided, it should be pretty obvious what's going on here. So what we're trying to find out is, well, we have a circuit. We have one resistor, that's R1, and then we have another resistor, R2. And the idea is, and then like there's this whole other circuit going on. There's a triangle here, there's a square here, some weird circuit elements. Whatever we want, we can put a circle here. These just stand for arbitrary circuit elements, just to reiterate. Let's say there's R3 here. And we're trying to figure out, like, let's say we don't care about what's going on in this place. And we want to figure out how these 3 resistors act together. Like, we just want to replace them with a single resistor because they look pretty simple, like they're just right next to each other. Maybe you can replace this with a single resistor to find a way to describe the circuit as a whole. Well, we're going to use Kirchhoff's laws. Specifically, we know that the current here is the same as the current here, is the same as the current here. And so the voltage drop across all of this is IR1 plus IR2 plus IR3 equals the negative, like it's the voltage drop. And so what's going on here is that we can actually factor this IR1 plus R2 plus R3 equals negative delta V. And what this is really saying is this looks a lot like a resistor with resistance. Effective resistance R1 plus R2 plus R3. And so this is the series rule. The R effective for some, like, let's say there's like a bunch of resistors, just sum like all of the resistances. And now we have to discuss parallel resistors. But before we do that, it's important to know what exactly is going on with series resistors is that the resistors are directly combining these 2 nodes. So there's nothing else in the way here. So between these 2 nodes, all it is 3 resistors in a row. If there was some other resistor over here, let's say there's a resistor over here, we just made a connection here. The series rule will no longer work between points A and B, but it would still work between points like C and B, because these 2 points are still just connected by 2 resistors. But we're going to erase this mess of diagram and go on to the slightly harder case, which is resistors in parallel. So what are resistors in parallel. So this is what resistors in parallel look. Remember, again, we have whatever circuit elements we want over here. And we're trying to find the effective resistance. So we're going to replace this whole square, which I'm going to draw a dotted line, with a single resistor. Well, what's going on here? We know that the voltage difference from point A to point B is the same because they're the same. It doesn't matter which way you go, the voltage difference is the same. So let's say we have current I coming in here. Well, we know this is this has to have a current of I1, and this has a current of I minus I1. Let's say this is R1 and R2. Well, this is telling us that I1 R1 equals I minus I1 R2. And this means we can actually solve for I1, which is the current at the very top. And what we get is that I1 R1 plus I1 R2 equals I, or what is this? I equal R2 or 1 plus R2. I R2. Right. So what we're going to end up looking at here is, I believe, that the effective resistance here is actually equal to the effective resistance is R equals 1 over R1 plus 1 over R2. And I believe this is what we're looking at here, although I might be slightly mistaken. And so we're going to slightly gloss over this section because we have to cover a few more important examples. But the idea is that, let's say there's a point A here and there's a point B here, and there are some resistors in the way. There's some resistors in the way. R1, R2, R3. And the important thing to note is that between these 2 points, all we have is 3 resistors that are all subject to the same voltage difference. Then the effective resistance, we can make a big resistor, R effective. And R effective is, let's say this is like all the way down to Rn. The effective resistance is the sum, or it's 1 over the sum of 1 over Ri. So let me try to do this in parentheses just so it's very obvious. So for example, the 4 case would be 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. And so this is the effective resistance. We can just cross out these 4 and draw A, B, and the resistance here is this thing. Right, so yeah, so now we're going to be getting to a few examples that sort of show a few of the intricacies of the electrical engineering concepts we discussed here. And for the POTDs that you guys will be solving, we'll see some more interesting concepts like infinite circuits, but we won't really be going into that right here because I want to give you all a chance to try that stuff out. So the first thing we're going to be showing is this circuit. We're going to be drawing a triangle. And we have a resistance R1 here. Let's draw this. R2, R3, R4, R5, R6. Points A and point B. And we are trying to find effective resistance between.
Hey, Hari, I can't hear anything you're saying. 1 second. Okay, could you say something now?
Hello, is this more audible?
Yes, that's better. Okay, please continue.
All right, yes. So, yeah, sorry about that slight delay. So what we have here is that between points A and point, we're actually going to move point B a little bit just to make this a bit easier to comprehend. We're going to move point B over here. And so what we have is a circuit. Let's say there's some circle, square here. There's a triangle here. And we're trying to find the voltage difference between A and B. So what we really have to do here is see that this is really just, wait a second, there's something slightly off here. Give me 1 second to figure out what exactly is going on. Right, so the first thing we should note here is that this question is sort of a trick question because I don't know why I include this in my notes, but these 2 points are connected by a wire, and so these points have to be at the same voltage. But this example is instructive because we can sort of imagine that there are resistors here, and so this problem would make sense. But they all have resistance of zero ohms. So that's just a quick sort of, I guess, sort of contrived example to show you what's going on. We'll see more of the same sort of contrived examples here. So the first second contrived example we're going to be showing is this example over here. And it's always important to have a few contrived examples here, just so you aren't like confused on what's going on when something weird happens. So let's just say there's this thing going on here, and we're trying to find, we're going to convert this circuit to circuit like this, R effective, and we're going to convert it like this. So what we're really trying to find is what is the resistance of all these things to make it so that it has the same current. Or in other words, what we could say is, let's say this battery has a voltage of 10 volts, and you could be asked to find the current here. So what we're going to be doing here is, the first thing to note is that it does not look like a series or a parallel connection. But what you'll note here is that the R2 here is a bit of a weird one because R2 is going this way and there's a wire over here. And so what we're going to do is we're going to make this into a problem we know how to solve. And we do that by inserting in the wire a 0 ohm resistor, which is fair because the wire is, in fact, a 0 ohm resistor. Sorry for slightly being out of the camera frame over there. Yeah, so now what we have is between this point A and this point B is a parallel connection, right? Because both these resistors go through the same voltage difference, and so the effective resistance of these 2 resistors combined, which we're going to simply replace by this big resistor, is 1 over 0 plus 1 over R2. And this is just infinity, and so this whole thing becomes 0. And so what this means is that this whole R2 from before is just sort of a defect, a bug. There was no R2 to begin with. The current isn't going to go through there. And what we really have is a wire. And the effective resistance is R1 plus R3. And the last example we're going to be looking at here today is this circuit over here. So we have, and this one is a bit more standard, just to sort of make sure we understand what's going on with series and parallel connections. Right, so we have this set of resistors, and let's just put like a battery over here and label these resistors R1, R2. And usually you'll be given values in ohms for these resistors, but we're going to be omitting those today, R4 and R5. Let's call this delta V. And we're just trying to find the current. Or what they really ask you for in these situations is the effective resistance of this whole thing, which is just a way of saying find the current and then calculate V over I. So that's what they really want you to do in these situations, is just find the current and calculate V over I. And you'll find that V over I is actually independent of V. So that's why they ask you to calculate V over I. So we're going to find V over I. So the first thing we're going to do is note that these 2 points, I'm going to mark them with X's now. Just checking to make sure I'm still sharing screen, and I am, yes. So these 2 points that are marked with X's, R1 and R3 are in parallel. So we can replace them with big resistor, let's see, 1 over R1 plus 1 over R3. We can just do this. We can just replace it. Now, we're going to note that, what are we going to know? We're going to note that this whole thing, there's this open wire over here. And so the current, this is sort of a shortcut that you'll often use. The current is always going to go through the path with no resistor from this point to this point, rather than go through resistors. And this will be seen in the parallel formula. For example, you have like 1 over 0 plus 1 over whatever is just going to be equal to 0. And so we can replace this whole segment with a straight wire. And then we have this important moment here where you do have to travel across R4 here, because let's say we're going through the circuit, we do have to travel across R4, but then we can skip R5 and come back here. So the effective resistance is just R4. Now, one last quick note before I'm going to leave you here today, just to make sure that I've honed in on how to sort of replace resistors with their parallel and series replacements. So I'll just be drawing this quick circuit over here to show you that you can, in fact, replace them in a very intuitive manner. And so give me the slightest seconds while I draw this circuit. So we'll work with this circuit. So what we can do here is we'll replace, let's label these R1, R2, R3, R4, R5. And you know what? We can even do, no, this is fine for now. So what we're going to do is we're going to replace R1 and R2 with the single resistor R1 plus R2, right? And now these two resistors are in parallel, so we replace them with the parallel formula, which is, I believe, it is 1 over R1 plus R2 plus 1 over R3. And this is in series with R4 and R5. So what we end up with is that the effective resistance is the series formula applied to this thing over here, plus R4 plus R5. And so as you see, we can just replace resistors with their series / parallel replacements. We don't actually have to like treat it in the theoretical sense or anything. We can just put it in there. Now, if they ask you to find, for example, the current over here, you can't just replace everything with a big effective resistor, because you actually care about what's going in between the things that you would otherwise replace with a big resistor. Yeah, so thank you very much for coming to this lecture, and I hope you all are extremely excited for the POTDs. Thank you.